quantum computing. What I'm going to try and do is take a little bit of a step back and focus on two things. There's absolutely no reason for us to be mystified by this concept. I'll try and sketch out why we ought not to be confused. And then I've been asked to focus a little bit on the impact on how things might change in the energy sector. Before I do that, though, I wanted to take a little bit of a step back and comment just on something which occurred to me during the last speaker. There's a conversation that has arisen a little bit like wildfire in the last 8 to 9 months due to a book written by Shoshana Zuboff. I don't know if any of you have heard about it. It's called Surveillance Capitalism. And it brings together a lot of themes that were being discussed just now. And it does so in a manner which really touches us in our hearts. I come from a generation where we have endowed these problems to our children and the people who are younger than us. I'm 55. And these issues speak to me more clearly now than they ever did during any part of my life. I wish I could be speaking about that rather than quantum computing, but I'm going to focus on quantum computing. But Shoshana Zuboff's book is extremely interesting. And there's one reminder. ExxonMobil, for example, has a market value of, I can't remember what, $300 or $400 billion. There are 6 or 7 companies that have nothing to do with natural resources that have market values way in excess of that, whose influence on our lives is much greater than any influence that was exhibited by oil and gas and hydrocarbon extraction companies over the sweep of the last century. So if you have a chance and if you're interested in what was being discussed earlier, then it's a fantastic little work that was done. Zuboff is Z-U-B-O-F-F. As it happens, I have the book in my thing as well. It's this big. I haven't yet got used to the idea of reading these things on Kindle, but Kindle's much more interesting. Okay, so quantum computing. If you look back, if we look back over recorded history, how many times have things happened that have really profoundly and fundamentally affected human life? It's very difficult to be precise because of the definitions, but if we use the word profound and fundamental, I would say to you that less than a dozen times. Now, of course, all the people that have ever lived, all the people who have ever lived have been alive or are alive now or in the last 25 years. So in some respect, the things that have profoundly affected humankind can only have happened in a short period of time. But what we forget is that if I had a line of my forebears, my father, my grandfather, your great-grandfathers, we wouldn't go very far back before we got to the beginning of recorded history. The invention or the discovery of fire, the wheel, the Industrial Revolution towards the end of the 18th century and the early 19th century. I'm originally from Lancashire, up in the northwest of England, which is where the spinning jenny was invented. And these things did have a profound impact. It was a hop, skip and a jump from the spinning jenny to the steam engine, from the steam engine to electricity, horseless carriages, and then from there to electricity, and the cable across the Atlantic, the acceleration in the way that we add nitrogen or actually enhanced nitrogen-based fertilizers into our soil. And then Turing came along and Shannon. We get the Turing machine and computers. So just as the vast population of humankind has expanded in the course of this last century, less than a century in fact, so these profound impacts have been concentrated in that period of time. And about 6 or 7 months ago, there was an article. There have been many, many articles now about quantum computing. They don't affect your lives on a day-to-day basis. But there was an article a few months ago, and it had a title which said, "The Real Industrial Revolution." And this is what we are living through today. The younger people in this audience are very privileged. When in 100 years' time, histories are written about today, This is the time when the single biggest impact on humanity will come to have a force. This is what we're talking about. These are big statements. These are big statements. I would encourage you, if you haven't yet looked into this, there's plenty of resource. At the end of my little talk, I'll tell you or guide you where you might find more information. So the first thing I'm going to do now is talk a little bit about the context of quantum computing. Then I'll explain why it's different. And although I've been asked to focus on energy, I'm going to focus on stuff that actually matters. Why? Yeah, why? Look forward 10 years or 20 years. We will have the ability, humankind will have the ability to convert the air that is around us into energy. The marginal cost of energy will be zero. The cost of production of energy will be zero. Right? We're not talking 100 years from now. Within 5 years, the 70-year-old process by which we burn or use between 5 and 8% of all the energy that is extracted from this earth into a fertilizer, that process, Haber-Bosch, which hasn't changed for 70 years, will change because of quantum computing. Now, the little addition of the word computing at the end of quantum puts people off. Who here is a scientist or is a computer scientist? Any people? So, well, we at least have maybe 3% of the audience, maybe a few more who are familiar with this. And with apologies to you guys, we're going to take things in little baby steps, which is the only way I can operate at my age, and really look at this from the point of view of accessibility. When we think about quantum computing, the word quantum is quite often misunderstood, partially thanks to James Bond's film, or the film about James Bond, what was it called? Quantum of Solace. And we kind of think about quantum as big. Technically, quantum means very small. Quantum is the smallest, typically in science, unit of matter or energy, or measurable impact. Our human mind is very good at big things. Right? So we look at the skies and we see the horizon, and beyond the horizon in the evening, as last night we see the moon. And we can understand that. And then we see the sun, and we can understand that. We're told that there are planets in our solar system. And when we're told that perhaps there might be 100 or 200 billion solar systems in this galaxy, we kind of get that. We kind of get it. It's big, but we kind of get it. And then when we're told that there are an untold number of galaxies, not a few, not a dozen, not a million, not 100 million, trillions of galaxies out there, we can still kind of get that. Now, our superstructure, this exosystem that the chap before me talked about, it's equipped to get it. But what happens when we go down? What happens when we go into the infinitesimal? We lose it. By way of example, how many atoms do you think there are in an apple? Now this gets a bit tricky, but this next bit you can bear with me. We're going to run out of time, aren't we? Okay, it doesn't matter. Well, it does matter. I'll stop when they tell me to stop. But think of this. In an apple, there are as many atoms as there are blueberries in what? Maybe in this room, you know what a blueberry is. Everybody knows what a blueberry is. Not this room. Perhaps if you were somehow to have a cuboid that is the area of Norway or Europe, as many blueberries as they could be fitted into that? Absolutely not. If you took the whole Earth and you filled it with blueberries, you would not have as many atoms as there are in an apple. But these atoms exist. And at the atomic level, We're not going to get technical in this talk. At the atomic level, the rules are different. The rules of the universe are different. I don't have anything here that I can throw, but young Bard, here, catch this. Right, now, that followed a rule. There was a little parabola, there was a bit of force, that had mass. It was a pencil, by the way, thank you. Chucked it at Nicholas, he caught it. Why did I know he'd catch it, apart from that he's an athletic young man? Because it followed certain rules. These are Newtonian rules, these are rules that Einstein uncovered for us. These are rules by which the universe works. But actually what we discovered about 100 years ago is that these rules are not the fundamental rules. The rules of quantum mechanics are what govern the universe. And at the quantum mechanical level, everything is different. Now, we're going to shift gears a little bit, fast forward to quantum computing. Just remember, the rules are different. About the early 1980s, a very fantastic scientist, actually 3 or 4 people at the same time, came up with this idea of quantum computing. Richard Feynman, a Nobel laureate, American physicist, and roughly at the same time, Yuri Manin, a Russian scientist, a physicist and mathematician, and a fabulous British scientist by the name of David Deutsch. It sometimes happens in history. I mean, if you go back to the 17th century, Newton and Leibniz came up with the idea of calculus at roughly the same time. So these 3 fantastic scientists came up with the idea of a quantum computer. The reason that their paths converged is a fascinating story in itself. But basically, when Richard Feynman was looking at this, they were looking at issues of heat dissipation. What I mean by this is when you have a computer and you pump some sort of energy into it, electricity, it consumes the electricity to do things. It doesn't matter what those things are, and it gives off heat. So how much of the energy that you're putting in can be maintained in order to provide a result at the end? These were the kind of things that they were thinking about. We still think about them. This, sir, you've got an iPhone there, right? So that, well, put it up there like that. Yeah, yeah. So everybody knows what that is. How many transistors in there? How many gates? Come on, wild guess.
100 billion.
How many?
100 billion.
Billion or million?
Billion.
Not yet, but 8 billion. 8 billion in that little thing there. Actually, most of that is just framework and chassis. The chipset that has these transistors, 8 billion, right? These things are physical things. They have to be controlled. They're controlled using something called Boolean logic, primarily the way in which we manipulate these things. Again, it doesn't matter what this means. But all these wonderful things we do on our iPhone are a fraction of what we could do. They're a tiny fraction. There's probably 3 dozen algorithms, and everybody retools them to do different things. Whether you're watching a video, or whether Netflix tells you to watch another video, or whether Amazon tells you to buy something that you perhaps wouldn't have bought otherwise. These are all, and also calculators. These are all the same handful of things. The majority of what we want to do, we cannot do with computers. A quantum computer doesn't operate on those rules. And from the time of the first concept coming along in 1980 to the last 3 or 4 years, this dream has become an engineering reality. And Feynman described this as a computer that computes the way nature computes. So why should we care? In 2013, the government of the United Kingdom instituted a National Quantum Technologies Program. Late last year, the Americans rushed a bill through Congress, and it had unanimous support, bipartisan support, and it was the US Quantum Initiative Bill. In China, in 2013, for that particular 5-year plan, and forgive me, I can't remember whether it was the next one that was coming or the plan in place at the time, but these things are easy to check. You've all got Google. Quantum computing was the #1 priority. It wasn't population control, it wasn't water. The European community has issued a flagship program for quantum computing. Why is everybody doing this? What is it about quantum computers that makes things like this happen? Google's annual R&D program is over $20 billion a year. The number one item that they've been spending money on for 9 of the last 11 years is what? Quantum computing, not driverless cars or anything else. Microsoft started its program in 2004. I could go on. Why is it that all these people are interested? So now we get, hopefully, closer to this issue of energy. Quantum mechanics, I mentioned with the help of Nicholas here, the rules are different. I'm not going to go into why the rules are different. If you want 3 tag words, there are fantastic videos all over the place that will help you understand this if you really want. But there are 3 aspects of the rules of nature that do not occur outside the microscopic. There happen to be entanglement, superposition, and interference. It really doesn't matter for this audience. These things mean that a quantum computer breaks the boundary of what could previously be done. And I'm going to focus on 4 examples of what I mean by that. All materials, everything from the coat that you wear, I've got a bit of a cold, so I took some paracetamol, to the paracetamol I ate, to this water on the jug here, everything is a material. It follows certain rules. Up until now, creating a new material was virtually impossible. We have alloys, which we found out a few thousand years ago by accident. But apart from that, creating a new material, if you know what the quality of the material is that you want, how do you start off? These are quantum mechanical processes. An example. I started off by suggesting that we might be able to convert light into energy. We all know how that happens, right? Everybody knows that. It's a photovoltaic process. All these converters on the top of roofs or even these solar farms. How efficient are they? How do they work? How approximate are they? This will be transformed. A quantum computer will simulate, through quantum mechanics, a material that not only increases the efficiency of the conversion of light into energy, but also, even before we get to that, battery power will be transformed. Transmission cables will be transformed. It's just 3 areas, 3 minor areas. What's bigger than that? The human genome. I'm not even going to get into the ethics and morals of that. Everybody will have an opinion. For the first time in human history, we not only can map the genome, we can manipulate it. Artificial intelligence. What we have until now is not even worth the name artificial intelligence. It's not even a vague approximation. Now, there are some people who worry. They say that these machines will create some sort of sentient being. The cortex there at the back of our brains is a quantum mechanical process. Some people, like Stephen Hawking, used to think that actually nature is one large quantum computer. Sadly, no longer with us. These are the things that we will encounter in a very, very short period of time. We're not talking now about 100 years from now. The first quantum computers now exist. The first programs that do some of the things that I've been talking about have gone from theory to reality. Nicholas, am I in good shape?
You're in good shape.
20 minutes. Oh, how many?
10 minutes.
Oh, brilliant, okay. So these things are a reality. So I'm going to dive a little bit deeper, therefore, into perhaps one of those little sideways. And these are the things that are happening right now at the moment. So let me give you one example of how this could happen. So in the current world that we live in, if I were to do 10 things, it would take me 10 steps. So if I were to shake hands with you and you and you, and I would carry on so that I had 10 people, and the only thing I was interested in was getting your name, then I would have 10 names. 10 shakes of a hand, 10 names, right? A quantum computer, because of the three things I mentioned earlier, superposition, entanglement, and interference, spits out a formula which allows me to handle not 10 pieces of information, but how many? 2 to the power 10. 2 to the power 10, 1024. It actually gets slightly more weird than this. Quantum mechanics, Feynman famously said, we actually don't understand why it works. We don't. We know what it does. It's one of the most experimentally proven rules of nature. In university laboratories, within a few kilometers of here, you've probably got, I don't know how many universities there are here, but you've got at least 5 or 6 labs where they do these experiments every single day, and they've been doing them since the Second World War. So it's not that we don't understand the what, we don't know the why. Encryption. We all worry about encryption. So I send a message to you, and what is encryption? So encryption is, I could either write it down, I could give it to a trusted party, and it could give it to you, and that might be safe. In this day of electronic communications, encryption is more sophisticated. But all encryption is about taking a message, scrambling it, and then putting it back together again. That's all it is. It's very complicated the way they do it, and the most common way of doing it includes mathematical algorithms. Nothing that is currently used could withstand a quantum computer. Nothing. It's not even that it's kind of secure, it's absolutely insecure. A quantum computer will have a profound impact on the way that we communicate. These are not things which are unknown. Again, if you, for example, the IBM website, the Microsoft website, there's fantastic videos that you can learn about. And I'll finish on the issue of energy. Even before we get to free energy, large energy companies are very focused on data and understanding what that data means. Multi-reservoir oil fields are optimized in an approximate manner in this day and age. A quantum computer using machine learning techniques will transform the ability of these companies to manage those wells. So in every aspect of computational capability, we're not talking about small or incremental change. We're not talking about disruption. We're talking about something that is fundamentally different. My children, your children, are inheriting a world where this industrial revolution, and I think we probably shouldn't call it an industrial revolution, is like nothing that has ever happened before. And that is why I think that your organizers asked me to come and speak to you today, and that's why suddenly very many people are interested in quantum computing. I'll stop there because there may be some questions.